This is a set of 3 worked examples that relate stoichiometry to issues of molarity and concentration. These are the kind of synthesized problems that combine ideas from different parts of the course and are more difficult as a result. So in this first example, we are given a balanced chemical equation. Notice that this is a double displacement reaction. So another thing that could have been combined into this problem is to have just given you the reactants, have you predict the products and balance the chemical equation. But in this case, I've given you the balanced chemical equation. And the question is, what mass of magnesium hydroxide can be made from 300 milliliters of 1.2 magnesium bromide, so that's our first reactant, and 400 milliliters of 1.5 molar KOH, potassium hydroxide, our second reactant. So let's concentrate on part A. This is actually a limiting reagent problem because I've been given information about 2 reactants, and so I need to figure out which one I'm going to run out of first. Just like in previous limiting reagent type problems, we have to figure out how many moles of each we have. So what I'm going to do is I'm going to say that I know that there are 1.2 moles per liter of magnesium bromide, and I have 0.3000 liters. And so that gives me 0.36 moles of MgBr2. This number makes sense to me because I have less than a liter, and what the molarity tells me is that when I have a liter, I have 1.2 moles. So if I have less than a liter, I should have less than 1.2 moles. So that's how many moles of magnesium bromide we have. For potassium hydroxide, we've got 1.5 moles per liter of KOH. And in this case, we have 0.4000 liters. And so we end up with 0.60 moles of KOH. All right, so now that we know how many moles of each of our reactants we have, we need to recognize that we know from the balanced chemical equation that for every 1 mole of magnesium bromide, we need 2 moles of potassium hydroxide. So at this point, the problem becomes a limiting reagent problem like ones we've seen before, where we are starting with the number of moles of each reactant. So I'm going to pick one of them, my 0.36 moles of MgBr2, and figure out how many moles of KOH would I need if I was going to react all of this magnesium bromide. So I'm going to use the stoichiometric coefficients from the balanced chemical reaction. So I know that for every 1 mole of MgBr2, I need 2 moles of KOH, potassium hydroxide. And so that means that 0.72 moles of KOH are needed. Now, we don't have it, right? Because we need 0.72 moles, but we only have 0.6 moles. So therefore, KOH, oops, that's not what I wanted to do. KOH is the limiting reagent. Okay? So now we know what the limiting reagent is. What we still need to figure out, though, is what mass of magnesium hydroxide. So magnesium hydroxide is one of our products. And so as in other limiting reagent problems, we start with the moles of limiting reagent, which again is our KOH, 0.60 moles of KOH. And now we relate the moles of KOH to the moles of our product that we're interested in. So we can see from the balanced chemical equation that there are 2 moles of KOH. Every time 2 moles of KOH react, we get 1 mole of magnesium hydroxide. So that means that we are going, oh, I didn't actually do that. I'm just going to go ahead now. Notice that this is going to give me moles of magnesium hydroxide. I'm asked for the mass, so I'm going to go ahead and convert that to mass using the molar mass of magnesium hydroxide. So I have gone ahead already and added up all of the masses of magnesium and the 2 oxygens and 2 hydrogens. And what I get is 58.33 grams per mole of magnesium hydroxide. And so what I end up with is 17.499 grams, or 17 grams of MgOH2. So let's make sure that makes sense. What mass of magnesium hydroxide? So we've got a mass, and we built it off of the moles of our limiting reagent, and we figured out our moles of limiting reagent by comparing the moles of each starting reactant, but using the stoichiometric coefficient. So let's look now at part B. What is the final concentration of potassium ions in solution? Whoops. In order to figure that out, let's get some more room down here. We need to recognize that, just draw a line, so now we're in part B, all the K plus ions that we started with are still present at the end. So let's go back and look at the reaction for a second. So we start with some potassium hydroxide that's dissolved in solution, right? It's aqueous. And in the products, all the potassium ends up as potassium bromide, which really, in this case, potassium and bromide are spectator ions. So all the potassium we started off with was really present as K plus when we started, and it's still present as K plus when we finish. So what we need to figure out is, if all the K plus ions are still present at the end, how many do we have? Well, we know we started with 0.60 moles of KOH, and since there's only 1 mole of K plus in each mole of KOH, that means we have 0.60 moles of K plus ions. That's what we started with, and that's what we end with, because it's just a spectator ion. Now, to figure out the concentration, we need the moles per liter. So we need to figure out what is the total volume, so we can take the ratio of moles to liters. So the total volume is 0.3000 liters plus 0.4000 liters, because that's what got added together. So we have a total volume of 0.700 liters. So the molarity, or the concentration, of K plus is equal to the moles, 0.60 moles of K plus, divided by the volume, 0.70 liters. Whoops. Let's keep our sig figs here. 0.700 liters total. And so that comes out to be 0.85714 moles per liter, or 0.86 molar K plus. Let's ask if this makes sense. So this 0.86 molar K plus, let's compare that to the concentration of potassium ions when we started. Whoops. So what we know from the start of the reaction is that we started off with 1.5 molar KOH. In other words, 1.5 molar potassium ions, K plus, per liter. Because we essentially diluted this by adding 300 milliliters of other stuff, now we have a lower concentration of K plus than what we started with. And that makes sense because it's the same number of moles of K plus in a larger volume, so it's more dilute. Okay, let's look at another example, slightly different this time. What we have in this case is 75 milliliters of 1.0 sulfuric acid, H2SO4, and it's going to react with 100 milliliters of 1.25 molar rubidium hydroxide. And we want to know how many moles of water will be produced. in this case. And I'm not asking for mass, I'm asking for moles. And there will be a second thing, which is assuming a density of 1 gram per milliliter of water, we want to know how much does this change the total volume of the system. So let's start with the first part. If we've got these two reactants, again, recognize that what we've got is a limiting reagent problem. Because we're given information about two different reactants, we've got to figure out which one is going to run out first. But in order to do that, I have to figure out how many moles of each that I have. And so I'm going to start with my sulfuric acid, and I'm going to say that I've got 0.7500 liters times the concentration, which is 1.0 moles per liter, right? Because moles per liter is molarity. So I end up with 0.07500 moles of H2SO4. And now I need the moles of rubidium hydroxide. So I'm going to say that's 0.10000 liters times its concentration 1.25 moles per liter. Because remember, molarity, this 1.25 molar is just moles per liter. Okay, and that gives me 0.125 moles of rubidium hydroxide. Okay, so now that we know how many moles of each we have to figure out which one are we going to run out of first. And it might be that you can eyeball this one, but I think it's always good to know how to do the reaction, or the calculation. So I'm going to pick the rubidium hydroxide this time. I'm going to say, okay, if I have 1.25 moles of rubidium hydroxide, whoops, how many moles of sulfuric acid would I need? And I know from the balanced chemical equation that for every 2 moles of rubidium hydroxide that react, 1 mole of H2SO4 react. And so that's going to give us 0.0625 moles of H2SO4. Now, let's think about what that is. This is the moles of H2SO4 that are needed if we want to react all of this rubidium hydroxide. Right? This is the moles we have. This is the moles that would be needed. Notice that we need fewer moles than what we have. So we have enough H2SO4. So if we have enough, then that's not the limiting reagent. So therefore, the rubidium hydroxide is the limiting reagent. Okay, now the question asked for how many moles of water, which is a product. So we, as is always the case, we're going to use the moles of our limiting reagent, which is rubidium hydroxide, in order to figure out how much of our product we can make. 0.125 moles of rubidium hydroxide. I'm now going to relate that to the product, and what I can see is that for every 2 moles of water that are produced, 2 moles of rubidium hydroxide would have reacted. And so that, of course, then is a 1-to-1 ratio or a 2-to-2, and so that gives us 0.125 moles of water produced. Okay, so that tells us that if we have this amount of sulfuric acid and this amount of rubidium hydroxide, we're going to get 0.125 moles of water. Now, the question is, assuming a density of 1 gram per milliliter, how much does this change the total volume of the system? This is actually we haven't done something like this, so this requires that we think pretty hard about how to go from what we've got to that answer. So I'm just going to write down this information. We're going to assume 1 gram per milliliter. And just for the sake of things, let's make it 1.00, so we're not going to be sig fig limited. And I know that's not what was above, but I can change the problem in the middle because I can. All right, so what we want to know is how much does this amount of additional water change the volume? So I'm going to start with what I've got, 0.125 moles of water. I'm going to convert that to grams first. 18.02 grams per mole of water is its molar mass. So that's going to give us 2.2525 grams of water. And I can now take that and say, well, there is 1.00 grams per milliliter. So really that's going to be 2.25 milliliters of water. Now, the problem, let's go back to look at it, asked, if we assume this density, how much does it change the total volume of the system? So, whoops, that's not really what I wanted to do. There's a couple different ways we can answer this question. We could say something like the total volume when the two things were added together is 175 milliliters. So this adds 2.25 milliliters. And that would be a sufficient answer there. The other thing we could do is we could calculate the percent change by taking 2.25 milliliters and dividing it by 175 milliliters and multiplying that by 100 to get a percentage. And so this comes out to be about 1.3% change. So we've increased the volume by a little over 1%. And those of you who are following my sig figs are going to recognize that it's not 1.3, it's 1.28% change. So the additional water that's produced has a small impact on the volume, but for the most part, when we add that amount of water, it's not a large change to the total volume of the system. Okay, let's do one more. In this case, we've got 3 moles of calcium chloride reacting with 2 moles of ammonium phosphate, producing calcium phosphate and ammonium chloride. And again, this is a double displacement reaction that I could have just given you the reactants and said, write me a balanced chemical equation and predict the products. Actually, predict the products and then balance the equation. So in this case, it says if I have 100 milliliters of 1.33 molar calcium chloride, so we've got information about this, how many milliliters of 0.85 molar solution of ammonium phosphate will I need to react all the calcium chloride? Now this might look like a limiting reagent problem because it mentions both reactants. However, we're not given enough information about the second reactant to calculate the moles outright. And so this is actually not a limiting reagent problem. This is telling us we want to react all the calcium chloride. So how much ammonium phosphate should we add so that we have exactly the right amount of each reactant? To do that, we're going to need to figure out how many moles of calcium chloride do we have. If we know the moles of calcium chloride we have, we can figure out how many moles of ammonium phosphate we need. So let's figure out how many moles of calcium chloride we have. We have 1.33 moles per liter of calcium chloride. And we know that the volume that we have is 0.1000 liters. So that gives us 0.133 moles of calcium chloride. That's what we have. Now to figure out how many moles of ammonium phosphate we need, we're going to take that 0.133 moles of calcium chloride, and we're going to look at the balanced chemical equation. We're going to say for every 3 moles of calcium chloride, we need 2 moles of ammonium phosphate. So for every 3 moles of calcium chloride, we need 2 moles of NH4 3PO4. And so what that gives us is 0.088667 moles of NH4 3 PO4. Sorry, that's a little messy. This is what's needed. Okay, so this is the number of moles of calcium chloride we have. We know they need to react in a 3:2 ratio, and so this is how many moles of ammonium phosphate we're going to need. Now what we know is that we have a 0.85 molar solution of ammonium phosphate. So now we can use that information to figure out how many milliliters of that solution we need. So I'm going to set up a proportion. There's several different ways to do this, but I'm going to say I want 0.088667, oh, and I didn't keep track of my sig figs here, moles, and I want to know how many liters do I need if I have a solution that is 0.85 moles in every 1 liter. So this is the solution I have, 0.85 moles per liter. If I want this many moles, I want to know how many liters would I need of that solution. So if I solve for x here, x comes out to be 0.1043 liters. And so because I'm asked for milliliters, I'm going to convert. It's going to be 1.043 milliliters. Rounded to the right number of sig figs, it would be 104 milliliters of NH4 3PO4 solution. So what we've just done is figured out what volume, how many milliliters of this solution would we need so that the reactants are present in a 3:2 ratio. The final question is, what mass of calcium phosphate will I get? In this particular problem then, we don't have a limiting reagent, but we know that we're going to use up all of these moles of calcium chloride because that's how the problem is set up. So we can use these moles of calcium chloride in the same way that we use the limiting reagent moles to calculate the mass of our product that we're going to get. So let's do that. We are going to take our 0.133 moles of calcium chloride, and we know that there are, in the balanced chemical equation, there are 3 moles of calcium chloride that react every time we create 1 mole of Ca3PO42. So I think I might have just said that wrong. This is the moles of product that we're going to get. Every time we make 1 mole of that, it means we've used up 3 moles of calcium chloride. And where I'm getting that is from this 1:3 ratio. Okay, so what we end up with, oh, nope, I did this in all one step. So because we're asking for the mass of the product, now we can multiply by its molar mass, which happens to be 310.18 grams per mole. That's the mass of calcium phosphate. And what we get is 137.5 grams. Rounded to the right number of sig figs is 138 grams of Ca3PO42. So what we're saying is, this is the mass that we would produce if we combined these volumes, this volume of that, and the additional 104 milliliters of our other reactant.